All right, let's dive into something that's literally all around us, but we barely ever think about it: gas. It seems super simple, right? But the truth is, the world of gases is packed with some amazing complexities that have a huge impact on everything, from how we power our homes to how we explore space.
So, to kick things off, I've got a kind of weird question for you. Picture this: you take a normal, fluffy marshmallow and you stick it inside a vacuum chamber. What do you think happens when we start sucking all the air out?
You might think it would just sit there, or maybe even shrivel up. But nope, the exact opposite happens. The marshmallow expands. It puffs up into this giant, puffy cloud. It's seriously wild to watch.
And that right there is the big question. Why on earth does removing the air outside the marshmallow make the marshmallow itself grow? To get to the bottom of this, we've got to zoom way, way in, down to the microscopic level. See, to really get it, you have to stop thinking of a gas as just empty space. It's not. It's more like an invisible, totally chaotic ocean filled with countless tiny particles that are constantly in motion. Now, there's a name for this whole idea. It's called the kinetic theory of gases. And it's basically a model that tells us a gas is just a huge collection of incredibly small particles, atoms and molecules. And they're all just zipping and bouncing around completely at random. Okay, so trying to track all that chaos would be impossible, right? So the theory starts with a few key assumptions to make things simpler. It pretends that the particles themselves take up practically no space, that they're always moving randomly, that they bounce off each other perfectly like tiny billiard balls, and, importantly, that they don't really interact with each other. It's a perfect, simplified little world. And believe it or not, this idea has been around for ages. Way back in 1738, this guy, Daniel Bernoulli, figured out that what we feel as pressure is nothing more than all those tiny particles constantly slamming into a surface. It's the combined force of trillions of tiny collisions. So how do you take all that microscopic madness and make it predictable? Well, that's where scientists and engineers got really clever. They built a beautifully simple mathematical model based on those perfect world assumptions. And here it is. It's called the ideal gas law. You've probably seen this famous equation before: PV equals RT. This thing is a cornerstone of physics and engineering. And the real genius of it is how it takes these three things we can actually measure: a gas's pressure, its volume, and its temperature, and connects them with a super simple, predictable relationship. It's just elegant. But here's the catch. In the real world, things are messy. Gases aren't always so ideal. And under certain conditions, this simple, elegant model, well, it starts to fall apart. So what's the big difference between ideal and real? Well, remember those assumptions? The ideal gas model says particles have no volume and exert no forces on each other. But in reality, gas particles do take up a little bit of space, and they do have tiny forces that attract them to each other. And those two little details change everything. So when does this really matter? It's when you push things to the extremes. Under really high pressure, you're squishing those particles so close together that their actual volume starts to count. And at really low temperatures, they slow down so much that those little attractive forces have a chance to grab hold. That's when the ideal model starts getting it wrong. So if the ideal law isn't always right, what do? Just throw it out? Nope. Engineers came up with a really clever patch, a way to correct the formula for reality. So here's our old friend again, the ideal gas law. Simple, clean, and, as we now know, sometimes not quite right. Now look closely at the new version. See that? They just added one single letter, Z. This little z is the magic bullet. It's a correction factor that bridges the gap between the perfect model and the messy real world. This z is called the compressibility factor. You can think of it as a reality check number. It's a factor that tells you exactly how much a real gas is straying from that perfect ideal behavior we talked about. And here's the key. If a gas was behaving perfectly, just like in the ideal model, its z factor would be exactly 1. And if z is 1, the equation just becomes the original ideal gas law, so it all fits together. So how do engineers find the right z value? Well, they don't just guess. They use these incredibly useful charts, like this one. By looking at a gas's pressure and temperature, they can find the precise z value they need to make their calculations dead-on accurate. Okay, I know, this might feel a little abstract. A letter and an equation, a chart, who cares, right? Well, it turns out that getting this correction right has massive, and I mean massive, real world consequences.
Just look at this example with steam. If you use the simple ideal gas law to calculate its volume, your answer is off by almost 6%. Now, that might not sound like a lot, but if you're building a $1 billion power plant, a 6% error is a catastrophe. But look what happens when you use the z-factor correction. The error drops to less than 0.5%. That's an incredible improvement in accuracy.
And that accuracy is absolutely critical. We're talking about everything from designing efficient power plants to making sure a scuba diver's lungs don't get damaged when they come up to the surface. Heck, even an astronaut's spacesuit has to be designed to handle the real behavior of the air inside it when it's exposed to the vacuum of space. The ideal model just isn't good enough when lives are on the line.
Which brings us all the way back to our marshmallow. It's filled with tiny bubbles of air, right? And that air is a gas. When we suck the air out of the chamber, we're removing the outside pressure. Suddenly, there's nothing pushing back against the gas inside the marshmallow's bubbles, so those gas particles push outwards, and the whole thing expands. It's a perfect, squishy little science experiment. So that's the deal with ideal versus real gases. And it kind of makes you wonder, doesn't it? What other ideal models do we use all the time? In our jobs, in our plans, even in how we think about the world? And where do those nice, clean, simple models start to crack when they run up against messy, complicated reality?